Okay, I want to talk about special relativity and general relativity. So, in special relativity, light is not actually subjected to special relativity. Only matter is subjected to special relativity. So, here I've got a b value of 0.6, meaning that matter is travelling at 0.6 c, and then on the right here I've done the calculation, so I probably don't need to explain that, but CT is gamma and CT primed is 1, and VT along the top is the speed of matter. And so you've got a light clock, and it's travelling to the right. That's the matter. It's travelling to the right at 0.6 c, I guess. Anyway. The speed of light is wavelength times frequency, so according to the relativistic slide rule I think that's the equation, because the speed of light actually drops depending on the medium, so it's always 1 over t, but in a vacuum 1 over t is 1. So the wavelength is the same as the velocity, so it's 1 over t as well, and then the frequency is a constant. The frequency doesn't change, and I showed in a previous video how you just move your finger up and down at a constant rate, and then you can either make that finger move off to the right or left, or you can keep it where it is, but the frequency doesn't change. It's the light clock, and the speed of light is the frequency, okay, in this case. So what about matter? Well, the speed of matter is L over t, and it can't exceed the speed of light, and so it's subjected to special relativity. So the wavelength is the de Broglie wavelength, and that's actually contracting due to velocity. So L is length contraction, and then the frequency is radians per second. Okay. Just showing how it looks there. And just one more thing, just show that. And that's a more extended version. And if I reduce that to 0.4, then I can put an undistorted picture of Gabor's basic concept for the holographic principle, and that's undistorted now because I'm using 0.4. And he's looking and seeing that the object B is there even though it's not there. I've already explained all that. I sort of adjusted my ideas on that a little bit. Anyon's a charge. So there you've got a negatively charged matter at the top. That could be an electron, and at the bottom you've got a positron, positively charged antimatter. and that's all I'm bothering to label. Oop, there it gets reversed. And now general relativity, I have to prove that it can do those calculations. So let's say you've got Mercury's precession. So let's put in the value for Mercury's precession, which is 000015971. And then you put in the semi-major axis, 5.79, 5.79 to the power of 10, and then you check it out. You see that it's going around the sun. Mercury's going around the sun, so that's the correct mass of the sun in kilograms, and that's the correct calculation for the arc seconds per century lost due to time dilation, which is what general relativity is added to the equation to explain Mercury's precession, because Mercury is so close to the sun that it starts to become noticeable, the fact that Newton's equations aren't working properly. And you can see the only thing you're using from the relativistic slide rule is b cubed. Then in brackets I put our man-made units, which is the speed of light and that distance, and then all that other stuff is just don't even need to worry about that other stuff. It just puts everything into years and centuries, into a century, and calculates the other stuff. So that's it. 42.98 arc seconds per century is the extra amount of precession according to general relativity, so that works out. Light bending, this is the first proof of general relativity. According to Newton's equations, this first of all, let me put in the what I need to put in. So the b value is 2 zeros, 14, 5, 6, 92. And I need to put in the distance, which is 69.57. So that's in meters. And what do we find? Yes, we find that the arc seconds is 1.75, which is what it is according to general relativity. And according to Newton, that 4 is just a 2. So that's what that's the only difference between Newton's equation and general relativity, is that the 2 becomes a 4 in general relativity. And the funny thing is, Einstein thought it was going to be a 2, but luckily the weather was bad and they didn't get to measure it, because otherwise they would have proven general relativity wrong according to his calculation, which was pretty funny. But anyway, he got it right in the end, and of course the mass is the same. It's the mass of the sun. There's photons getting bent by going around the mass of the sun. Okay, so general relativity is really just a topology. It's like a survey of the of space time. It's like a civil engineer is sort of figuring out the the topology of the land on the Earth or something. So it doesn't really explain anything, but it so here's my attempt at a explanation for why space-time is bending. So the bending here is so tiny you can't even see it, so I better put a nice big one. That would be a neutron star. So neutron star is bending space-time. Now I think I'll get rid of this extra stuff because it just looks really bad. So now there's an angle between there and there, and now that is actually space-time from there to there, that distance, and it's actually shortened because it's bent down. So you can see how topologically it was along the x-axis, and now it's bent down towards the center here. Here actually. Yeah, that is the center there. So, and this is its orbital velocity. So that's where the bending comes from. But it's Euclidean geometry. Yeah. What else? And then I'm going to upload this version because it's got extra stuff in there. Here of imagining you got the squared modulus of Schrodinger's equation is the actual one we observe, so I'm only bothering with that one, and but I don't really need those equations in there because you can still see how LB is linking these circles together, and how it's going to cause the wave function to collapse like that. See, all that, the entire wave front is just all the energies getting focused in on that one point here, which is the point where we observe the photon. So you can see how this that thing, which is L to the power of T here, and then I've graphed it on the Cartesian coordinates here. You can see that it looks like a probability density function. I mean yeah, and you can see how it just behaves like an uncertainty function, where the position is becoming more and more definite, and then as the wave function expands and the light expands out to a maximum of here it would be actually, you just end up with uncertainty as to the position, but more certainty as to the momentum. And then when it hits the screen somewhere, all the rest of the wave function just has to collapse onto that point, because the energy has to be conserved. So it's all got to collapse into that photon, and simultaneously it's going to disappear, the wave function, because it all collapsed onto that point.